Hello and welcome to our video 1 on acids and bases, where we discuss the properties of acids and bases and nomenclature. So keep in mind, we just learned in solutions that we express the concentration of a solution quantitatively in chemistry using molarity, big M molarity, which is moles per liter of solution, moles of solute per liter of solution. So when we show brackets, that's still what we mean. All the same content already learned is still being applied. Acids are compounds that produce hydrogen ions when you place them in water. Some common acids, and this is a diagram here of hydrochloric acid, which you see you have hydrogen and chloride ions in an aqueous solution, meaning what's not expressed there is water molecules, but it's understood. Some examples of common acids you may find around your house. Acetic acid is a vinegar. It's about a 5% solution. Citric acid is present in citrus fruits and juices. Sour candy is flavored with malic acid, fumaric acid, tartaric acid, citric acid, and several others. And that's what gives them their super tangy taste. And lactic acid is found in milk. Now, when you put hydrogen ions in water, it's not quite that simple. We discussed an ion called hydronium earlier in the year in nomenclature. In reality, when a solution contains hydrogen ions, what ends up happening is they end up combining with water molecules to make hydronium. Okay, and this complex is actually what we'll see really form in water. However, you'll see both of these things expressed when discussing the acidity of a solution. So look for both; they're interchangeable. Acids are sour in taste, hence our candies that are sour. They react to form hydrogen gas when exposed to most metals. There are metals that will not corrode in acid. They will turn blue litmus paper red. This is an example I'm about to show right now of a cartoon of that interaction. Let me back up here. This is hydrochloric acid and zinc metal, so I'm just going to drag one into the other, and you get hydrogen gas with zinc chloride. Um, so we see, keep in mind, this is blue litmus paper turning red in the presence of an acid. When you make an aqueous solution of an acid, it produces electrolytes. So if you were to put our conductivity meter or tester into an acidic solution, you would expect it to turn the light on. Acids react with bases to form salt and water. This happens when these are in perfect stoichiometric balance, meaning equal moles of each. You'll end up with zero acid or base. You'll only have salt water left in theory. So this is those cartoons I was showing a moment ago. Um, Acid nomenclatures, this is purely review. Keep in mind there are binary acids, which are when hydrogen is bound to a nonmetal. To name those, you'll use hydro as a prefix with the root of the anion and then add the suffix ic. So HBr is hydrogen and bromine, hydrobromic acid. Ternary acids are hydrogen bonded to a polyatomic ion containing oxygen. We call these oxoacids or oxyacids also. We're going to begin those by looking at the polyatomic ion bound to hydrogen without the suffix. Okay, so if we had something that ended in ate, we would add the suffix ic. If we had something that ended in ite, we would add the suffix ous. So HNO3, you have nitric acid, so that's nitric acid. HNO3 sorry, has nitrate, it becomes nitric acid. ClO2 is chlorite, becomes chlorous acid. So keep in mind a couple little phenomena that flummoxed people earlier in the year. When acid ion contains sulfur or phosphorus, the roots are sulfur and phosphor, respectively, not sulfur phos. So H2SO4 is sulfuric acid, not sulfic acid. H3PO4 is phosphoric acid, not phosphic acid. So we hope that helps you. Nomenclature with acids. Let me clear the text off this screen real quick because I'm going to go through that. Um, Organic acids are a type of acid that we won't really directly address in pre-Chem, but we may deal with structures and discuss them informally because they are common acids. Um, so acetic acid vinegar is one of them, and I think that's probably the best reason to get this idea out there. This is not going to be tested directly. You won't be asked to memorize any organic acids, but basically acids found on carbon chains. And when you see a carbon oxygen double bound and then a single bound oxygen off the same carbon, that's called a carboxylic acid group. And so anytime you see that structure on any chain, that's going to be a carboxylic acid portion of that molecule. Notice how we have four examples here: formic acid, butyric acid, acetic acid, and benzoic acid. You have different structures attached to it, but they're all different carboxylic acids. And it actually, this third column actually gives you sources of these things. Fire ant venom is formic acid. If you didn't know that, that's a good little factoid. That's one of the reasons you inflame so greatly when a fire ant gets you. It's basically injected an acid under your skin. Um, so anyway, nothing to directly memorize here, but some neat phenomena for you to look at. If you keep in mind, you guys learned all about organic molecules and biomolecules section of biology. You learned about amino acids, and an amino acid is literally an amino group and an acid group attached to a molecule somewhere. And the acid group is actually this carboxylic acid group. So every amino acid has this COOH appearance on the end of it. And the amino group is an amine group, NH2. So we'll get more into that in AP Chem. Acid strength is important. Strong acids ionize completely in water. So we're going to talk about that directly. This is hydrochloric acid in water making hydronium and chloride ions. This is, remember, hydrogens attach onto the water molecule to form hydronium. Okay, that's the same exact thing as saying a hydrogen ion, so please don't let that cross you up. They are interchangeable. Anyway, what you see is this thing completely ionized when you place it in water. So imagine we had a tube bubbling hydrogen chloride gas into this water. You would expect it to ionize completely, whatever dissolved. Weak acids do not ionize completely. This is sulfurous acid, and when exposed to water, we see some ions form, but most of that molecule, because it's polar, it stays in the water, but water is not able to overcome the strength of the hydrogen for the sulfite ion, so that stays intact. But it's still an acid because it still forms hydrogen ions in solution. There are three strong acids for you to know: hydrochloric, hydrobromic, hydroiodic. Any other binary acid is weak. And for example, the one that usually gets people, and this is, put a star by it, hydrofluoric acid is weak. Yes, it's hydrogen bound to a halogen. No, it does not totally ionize in solution like hydrochloric, hydrobromic, hydroiodic do. The reason is the strength of the bond between hydrogen and fluorine is sufficient to overcome water's ability to split it. So when you put hydrogen fluoride in water, water cannot uh, break that bond reliably. There are four ternary or oxoacids to memorize that are strong: sulfuric, nitric, chloric, and perchloric. Any other ternary or oxoacid is going to be weak. Know the strong seven. Bases, compounds that produce hydroxide ions in solution. I keep going back to my pen and it keeps getting me. Hydroxide ions in solution will be formed when you place a base into solution. Now, when we get a little later in the unit, we'll get to the theory behind acids and bases. Your molecule doesn't necessarily have to have, your base molecule doesn't have to have the hydroxide on it. It's also possible for a base molecule to make water split to form hydroxide, and we'll get into that too. Three examples I want to give you that you see at home potentially. Milk of magnesia is magnesium hydroxide. Drain cleaner is sodium hydroxide. And then window cleaners, ammonia, NH3. And if you notice, ammonia does not have hydroxide ions. Well, when you bubble ammonia through water, what ends up happening is you get ammonium ions and hydroxide ions, and they form ammonium hydroxide. Okay? Bases are bitter in taste. They feel slippery to the touch. They turn red litmus paper blue. Aqueous solutions of bases are electrolytes. They will react with acids in stoichiometric proportions to form salt and water. So same reaction we saw, same phenomena, neutralization reaction. Nomenclature for bases is basic ionic nomenclature, where we name the cation, then we name the anion. The anion is going to be hydroxide when it's an ionic compound. If it's not an ionic compound, like ammonia is not ionic, it's covalent, we're going to call it by its covalent name. Now, the only one we've ever memorized is ammonia, so the only one you need to memorize is ammonia. The rest are going to be hydroxide nomenclature. There will be other bases we'll look at and talk about, but the only ones you'll be asked to name are going to be the hydroxides and ammonia. Strong bases completely ionize in water. I'm going to rewrite that when we get to it. Strong bases completely ionize in water. That means all the base molecules that are dissolved form ions. All hydroxides in group 1 and 2, except beryllium, will form strong bases, and there they are listed for you. You see francium hydroxide omitted because it's not really going to be an element you'll ever find on Earth in any appreciable amount. Though some of the above, if you look at your solubility graphs or your solubility tables on your cards in class, your resource cards we use during tests, though some of the molecules you see there or compounds you see there are going to be insoluble or slightly soluble in water, when you do put a compound of that type in water, whatever little bit of it dissolves will ionize, and for that reason we consider it a strong base still, even though it doesn't dissolve well. What you will not have is intact chemical formula in water. It will all ionize what does dissolve. So, weak bases do not ionize in solution. They ionize only slightly. Okay? When we say slightly for weak acids and weak bases, we mean about, at most, 1 out of every 1,000 particles will ionize. That's very few. Okay, that's a good thing to keep in mind, that that's a small number, and oftentimes it can be as high as 1 in every maybe 10 million. So we get some very small values out of this when we say something is a weak acid or weak base. So all the above bases listed are not listed above are considered weak. Aluminum hydroxide, ammonia are weak bases. This concludes Acids 1, Properties and Nomenclature. You should have taken high-quality notes. Please rewatch any part of this video as many times as you need to get clarifications. Please come to class with questions you've got. We look forward to seeing you there.